will be sent out to whoever has registered for this event. For those of you just joining us, this is a Careers in Tech Summer Series session. Our start time is 6:30 p.m., which is in about 2 minutes. And then we'll get the show on the road. Welcome to a Careers in Tech Summer Series session by the Careers in Technology Initiative that is headquartered in IEEE Northwest Florida within the Computer Society and the Communication Society joint chapter down here. We have industry and academic partners that help us with getting this stuff funded and putting these putting together these types of sessions for various people, along with our more panel-oriented sessions as well. I'm grateful for our speaker for joining us tonight. And without further ado, I will go ahead and hand it off to him to begin his presentation.
Thank you very much for the introduction, Michael, and for the invitation to present to this group. So welcome everybody. My name is Nael Abu-Ghazaleh. I'm a professor at the University of California, Riverside, which is 45 minutes outside of LA, far enough to not deal with the traffic, but still in Southern California. And my talk today is on probing a little bit about what are the issues that we have to worry about when we build computing systems to support machine learning with respect to security in particular. So I want to start by a slide talking about a vision workshop that the computer architecture community had a few years ago with the idea to anticipate what is going to be happening in computer architecture in 2030. And I say architecture because I primarily work in that community, but really this applies to computing systems in general. So there is broad acceptance that Moore's law is ending. We have maybe a couple more ticks of technology before we have to either have a paradigm shift or accept that we can't keep shrinking transistors. And as a result, we're starting to see specialization at scale. So accelerators for important workloads or for groups of workloads like GPUs and NPUs and CPUs and so on, as well as deployment on the cloud primarily, especially for newer and more aggressive technology. And then machine learning emerging as the workload of the future. I mean, especially nowadays confirmed with generative models and large language models and things like that. So perhaps it's not the workload of the future, but definitely an important workload for the future. And since basically we're perhaps reaching the end of the road for silicon, kind of new paradigm shifts, quantum computing, DNA computing, and things like that, and then early entry through the cloud, and eventually perhaps, I don't know if we'll see a quantum computer on phones, but for other technologies, perhaps economies of the scale will help us get there. So given these trends, I want us to think about during the hour or however long I have with you about this intersection of these three areas. I want to start by first acknowledging that, of course, machine learning is disruptive and perhaps a little bit scary, and it's already outperforming us and outperforming handcrafted algorithms in many areas. But the credit doesn't go just to machine learning algorithms in its success and proliferation. A lot of it has to do with our ability to support these intensive workloads computationally. So I would say GPUs have just as much should get just as much credit for kind of the success of deep learning and machine learning as the advances in algorithms. So, already we hopefully are familiar with this symbiotic relationship between machine learning and, again, systems, I will say, not just architecture. So just like we use machine learning to optimize all kinds of things, we have a lot of opportunities to use machine learning when we build computing systems to kind of translate our ad hoc policies into things that are data-driven, that help us capitalize on opportunities that we might not see by just thinking about the problem. And as I mentioned, the success of AI and the success of machine learning depends on advances in computation that we as a computing community can provide to support, to continue to support the increasing demands from machine learning. But what is there at this intersection between the three areas? So when we think about security as well, what is it? What are the issues that we have to worry about? That's what I would like us to think about today. So before getting to this intersection of the Venn diagram, I think it's instructive for us to think about the pairwise intersection of these three areas. So first, looking at intersection of architecture and ML, I think I already mentioned, that there is this cross-pollination between these two areas, right? So the architecture and the systems communities, academia and industry, we all now think about like what we need to do to support machine learning workloads better, whether from hardware and sort of existing kind of models of hardware, or designing new ones, or thinking about what to do for real-time response or low power on devices or whatever. So a lot of our thinking as this architecture systems community focuses on supporting machine learning. And you see examples of hardware that's been developed to support that. So TPUs and NPUs and so on. But it's also true that we are leveraging machine learning for architecture and systems, both at all phases of the design and deployment, right? So we use machine learning algorithms in the design of architecture and computing systems, but also during operation and so on. So moving on to the intersection between machine learning and security, machine learning models introduce new security threats, new ways that people try to take advantage of them and attack them. So hopefully, some of these models you're familiar with. I'm just going to touch on them very quickly. And of course, there is also the feedback from machine learning to security. So security practitioners are also trying to leverage ML to harden system, to automate finding of bugs, and so on. But I want to talk a little bit more about these new threat models and new attacks that machine learning models offer to attackers. Okay, so a type of attack that has received a lot of airtime, and I hope many of you are familiar with it, is what are known as adversarial attacks. So in these kinds of attacks, if we have a classifier, for example, that classifies images, so you give it an image, it tells you what is inside of this image. The model has been trained to recognize with some confidence that this is a plane. But if I come around and sort of carefully craft noise patterns, and what that means, so there are algorithms that sort of back propagate through the network to find essentially the blind spots, if you want to think about that, of the ML model. So the ML model is just essentially a function fit to the data, right? So since the data is not exhaustive, there will be areas where that are basically, you can think of them as don't care, and the boundary between the classes in an image classification model might be loose. So if you manage to sort of shift your image into an area that the model doesn't know too much about, you might find blind spots where you can get it to look at this plane and tell you that it's a cat. And as a result, if this is sort of part of your pipeline and the adversary is able to manipulate it, they can really bring your system down, or cause a. So we saw, for example, the self-driving cars mistake a truck for empty space and crash into it, and so on. So they can abuse your classifier to their advantage and cause security and safety problems. And this can be applied in real time. So this is something that we did a couple of years ago, right? We showed that in real time, we can listen to a command to Siri or to a digital voice assistant, and then predict the rest of the sentence and craft adversarial noise to get the command that you're telling your device to change. So you still hear yes, but your machine hears no, or classifies the audio into no. And maybe this is not surprising, because like even our brains, which are neural networks, this is an example of a visual illusion. So if you look at this diagram, your brain wants to think that basically there's a black dot at every intersection. But once you focus on it, you see that it's not there. So maybe it's not so surprising that these neural networks have these kinds of weaknesses. So another kind of attack that people worry about is a privacy attack. So a lot of the time, the data that is used to train the model is either proprietary or private, right? So if you can think of medical data, you don't want the patient data to be out in the open, but at the same time, you want to learn from it to make your diagnosis tools better or whatever. So these privacy-based attacks try to determine whether what the data that was used to train the model is, or try, for example, one version of it is called model inference. So I have some images, or I might kind of try out a patient's record and then test out if they have a certain condition. And then I query the model, and then based on the output from the model, I'm able to tell whether that picture or that health record or whatever was part of the training set, and therefore be able to extract information about about the secret training data. So I'm not going to talk too much about this threat model, but I'm going to just sort of move on. Then a final model that I want to talk about is called a model extraction attack. And in this case, the machine learning model itself is secret sauce, right? So it's a private model that I trained with maybe private data, and even the architecture of the model is secret. So I want to deploy it and let people use it, but they're interested in stealing my model because that's where my IP is. That's where the value that I add is. And then the simplest form of these is I just query it many, many times, and then I use the answers that I get from the model to train a proxy model. So this is not sort of the exact model, but I can sort of learn how to mimic it, and then I don't need to use their service anymore. I can just use my own. And we'll see that there are ways to sort of accelerate that attack using kind of system level security vulnerabilities. And this is not too related to my talk, but I felt I cannot sort of move off without mentioning something about the security of generative models and large language models and so on. I think this is going to be the wild, wild west as far as security vulnerabilities are concerned. Already we see vulnerabilities. So we're eager to integrate LLMs into everything now. So attackers have an sort of multimodal input. So that means maybe images or videos or so on, not just text. So this is an example of a sort of a tool that takes as input YouTube videos. And then, I can do what is known as prompt injection attacks, sort of give it my own prompt just by embedding some text information inside of the video. And then this can also, so my tool could be, let's say, a recommendation tool. So I give it some information from a website, and it should be able to recommend to me like a good restaurant or something like that. So I can manipulate the prompts inside of my website to get the LLM to give you an output of my choosing, right? So there's very little to prevent these kinds of attacks, and there's quite a few interesting attacks that are coming up, but they're not related to architecture. So perhaps in the future I can make a talk about them. I just wanted to say that this is like a big concern. I mean, we're eager now to just plug LLMs into everything, but the security implications can be quite serious. They're almost a Turing, you can think of them as a Turing complete machine, right? So, they have memory, which is their context window. And then you feed them instructions, which is the prompts that you feed into them. And then you can really sort of sequence those to cause the, with some creative prompt engineering to cause the LLM to give you an output that is under the attacker's control. So we should be careful before embedding these in safety critical or kind of even systems. There's examples of getting them to manipulate users to give their credentials, getting them to sort of in a psychology-based assistant to really manipulate users into doing harmful things and so on. So it's something that we should be concerned about. So getting back to our topic, the final sort of two-way intersection of the Venn diagram is the intersection between architecture and security. And this is, I guess, an area that I spend a lot of time with my group studying. So we think about basically vulnerabilities that originate in the hardware, in the computer architecture. And I'm not going to get into details, but you might have heard of covert and side channels, speculative execution attacks. These are the the logos for the Spectre and Meltdown attacks that got quite a bit of news recently. Yeah, I'm sorry, 2018, 2019, I would say, maybe not so recently. And then fault injection attacks, if you heard of Rowhammer attacks, or even conventional physical fault injection attacks, where you take a device and you put it outside of its operating conditions, and then the faults that happen, you're able to exploit as an attacker, and so on. And then on the other side, we think about defenses that are rooted in architecture. And then, so I qualify these, or I think of these as two categories. One category is make sure that when you design your system, you're not engineering it to have these kinds of vulnerabilities that are there in this red box. So this is the do no harm. And then the other side of it is that software security is becoming a really computationally demanding workload. So we need help from the hardware to give us usable abstractions for security. So you might have heard of Intel SGX, or equivalent from other chip manufacturers, TrustZone or SEV and so on from ARM and AMD respectively. And then also like computational support for expensive defenses. So this is like, there's a lot of opportunities in this space. And, because security is such a big need, kind of chip manufacturers are investing a lot in this space. So getting to the sort of the three-way intersection in the Venn diagram. I'm sorry, do you see my full screen or do you see my presenter view? It just occurred to me that you might be looking at my presenter view, which I hope is not too annoying. Let's see if I do this. Would that work better?
We are seeing the full screen.
You're seeing the full screen. Okay, wonderful. Thank you so much. So the three examples, I'm going to talk about them because they're, I think, interesting on their own, but they are each maybe representative of a more general pattern, something that we would, think about when we're doing similar things. So first of all, the first pattern I want to look at is when we leverage machine learning inside of computing systems, not just architecture, then this machine learning is vulnerable to these adversarial attacks. And we have to think about what the implications of that are. And then on the other side, basically, how do we design machine learning that is robust against these kinds of attacks? The other pattern I want to look at is that, so we talked about the intersection of architecture and security, that there are these micro-architectural and hardware-based attacks. Can we use them to accelerate attacks on machine learning workloads, right? To be able to compromise the privacy or the model or something like that. And then finally, I'm going to go back to this intersection between the system and machine learning and ask, well, when we design accelerators and computing artifacts that help with machine learning, why don't we worry about security as well? And I'll show an opportunity to leverage approximate computing to make machine learning workloads kind of more resilient to attacks. So let's get started. So this is a fairly famous picture from 2016. The gentleman that you see is Lee Sedol, who at the time was the world champ in Go. And the common thinking was that Go is so complex that humans will continue to beat AI. At that point, we had like superhuman chess, and we could not beat the computer in chess anymore. By we, I don't mean me, but like Gary Kasparov and the GMs could not beat chess engines anymore. But at this point, basically, despite like fighting hard, Mr. Sedol was not able to beat AlphaGo. And then we were resigned that computers are just going to be better than us at these things, or AI is going to be better than us. But we ended up also learning, so human champions ended up learning strategies from AI. So maybe there is kind of room for cross-pollination. But I want to say that yesterday I saw a paper that developed adversarial attacks on these engines that allowed humans now to beat them. So we get the last laugh after all. But the kind of deeper lesson is that when you apply machine learning algorithms, even those that are fine-tuned and superhuman in their performance, that adversarial opportunity could still give an attacker a way to fool the machine learning model and then give them an advantage. Like in this case, winning against the superhuman engine. But if I have like something that controls a drone or or a self-driving car or something like that, it can cause a crash or worse. So as an example, I want to talk about some work that we did. I want to say starting maybe 2014, 2015, so close to 10 years ago now. If you remember, I mentioned that some of our work looks at how we use hardware to make systems more secure. So in this case, we, as well as a few other groups, were thinking about this problem that malware is like so prevalent, right? So these are statistics about what is known as malware volume. So the number of different malware samples that you see, and this is sort of 2021 and to 2022. So it's in the order of like 500 million different samples that you see every month. And this is not because we have like hyperactive set of attackers. We do, but they're not that active. It's because malware and sort of computer crime is a business now. They make a lot of money off of it. So they have all kinds of techniques that recompile the malware several times a day, do modification to it, and so on, to get past techniques like virus scanners and so on. So if you're constantly evolving, then these static techniques that look for signatures might not be able to find you, right? So detection is really hard. And then if I make my detection techniques more and more sophisticated, then they need more and more kind of resources. And then I'll find my system, all it's doing is just looking around for malware. And you see that also the type of malware changes over time, right? So this is so ransomware went down a little bit in 2022, but then now we have cryptojacking attacks and IoT malware. So it's sort of kind of an evolving landscape all of the time. So the idea behind these hardware malware detectors is to try to see if we can detect malware as a computational anomaly. So so basically, already most computing systems collect these, performance counters, you could call them, but these hardware events. And the typical use for them is for debugging, right? I want to see what's going on in my program and try to improve it and so on. But the idea with hardware malware detectors is to try to then take these sort of execution events and use them as a fingerprint of the program. And the hypothesis is that malware is going to behave differently than normal programs in this feature space, in this sub-semantic space. And we were not sure whether this will work or not, but we tried it out, and it actually worked really, really well. And there were a bunch of different people that sort of looked at different things, and a lot of papers that were published in many top conferences, which maybe doesn't mean a lot, but there was actually commercial adoption as well. So I think the first adoption I'm familiar with was at Qualcomm as part of the Snapdragon processor. But this is now like a big sort of feature within Intel processors called the threat detection technology, and Microsoft Defender uses it and so on. So it's essentially collecting these performance counters and then using AI runtime heuristics, so a classifier on top of them. And then once you suspect something is malware, then you invoke something that cleans it through the cloud. So now, again, the pattern that I want us to sort of think about is when I'm using machine learning as part of my system, can an attacker try to abuse it? And in this case, abusing it is trying to evade detection. So if I manage to deploy malware, but at the same time, it can work around this machine learning model and not be detected, then we failed, right? Then it managed to compromise our system. So we pursued this question in a paper we published in Micro in 2017. So it's fairly old. So I'll talk about like maybe briefly about another solution that we pursued more recently. So the first question is, can we evade detection? Is it possible to evade detection? So we did that approach where we query the model multiple times, and then based on its answer, so we run some normal programs, we run some malware, and then based on how it either detects or doesn't detect them, we build a proxy model of the detector. And once we find that model, then we can do these adversarial attacks on it, right? So remember those attacks where we add noise to our program to try to avoid detection. So once we reverse engineer the model, then we are able to come up with patterns of instructions that would fool it. We would still be able to do the job as a malware, but we are able to fool it. And then once we established that, the second question was, can we make it robust to evasion? And then we tried to do that using a technique called resilient hardware malware detectors. What we're trying to do is we make it provably harder to reverse engineer by adding some stochasticity in how it works. And again, the solution itself is perhaps not the point here. The point is we need to harden machine learning algorithms if we end up using them as part of our systems. Okay, so for the reverse engineering, we didn't know much about the hardware malware detector. So what we do is we test out different kinds of features, and then every time we're able to build a more accurate proxy model, right? So we query the hardware model. We don't know what it is. Every time, we guess that it's using this feature or that feature, and if we get like a better performance, that means we were correct, until we're able to kind of reverse engineer it with high confidence. And then after that, we train, we kind of are able to develop our adversarial noise. So inject some instructions that cause the malware, the hardware events to look different, and therefore avoid detection. So the reverse engineering was really successful. So the proxy models performed almost identical to the original unknown model. And the conclusion is that, it's easy to reverse engineer them. So, it's not, even if you hide the design, that's not enough protection against how the detector works. And now once we reverse engineer, we're able to go ahead and fool them. And here we had a challenge in that we wanted to take sort of actual malware from the wild and then modify it so that it can avoid detection. The problem with that is that the attackers are not nice enough to give us source code. Plus, the code is obfuscated and sometimes encrypted, and so they use a technique called packing and so on. So it was very hard for us to kind of get the program and then modify it so that we can produce the evasion. So what we did is we used kind of a binary rewriting approach to do our injection. So we run the code, and then every time it has a branch, we assume that it left a basic block. A basic block is just a group of instructions. And then right before the branch, we inject these extra instructions whose job is to shift the features that the malware detector is collecting. So if it's collecting, let's say, memory address patterns, then we create load and store instructions that change that pattern. If it's collecting instruction distributions, we add instructions that shift the distribution, and so on. And then once we do that, so we pick these instructions using, so after we construct the model, if it's, for example, logistic regression, we use instructions whose weights are negative so that we shift the value of the classifier to the other side. And sort of, there are different, so there are different gradient descent techniques for more complicated classifiers. At the same time, we have to make sure that the new instructions that we add do not affect the malware functionality. So there was a little bit of work to try to inject the instructions and then keep the malware working as not affect its state. And then as a result, once we inject even a single instruction with every basic block, the detection performance of the hardware malware detectors was just like gone. And if we did a random injection, if we just injected the random instruction, then there was no effect. Basically, it continues to detect. And the x-axis is the number of instructions that we inject per basic block. So the attack is really effective, and therefore we cannot just simply deploy these detectors. We have to think about hardening them against what the attacker can do.
I believe we have a question with regards to slide 33 in the chat.
Okay. Sorry, I don't think I can see the chat now. Is this approach similar to ROP injector? Yeah. So yeah, I think it's kind of similar. So in this case, it was an implementation convenience. We were not really. Yeah, I think this is the one where the memory image gets randomized, and then you sort of reverse engineer the image in real time and then adapt your ROP attack to that. If I'm not mistaken, this is what this is referring to. But if not, I apologize. Okay, yeah. So our problem in this case is not quite that, right? So if we were the malware developers, then we would be able to directly modify our code and make these changes. But this was more of an implementation difficulty because we were pretending to be the malware developers and working with actual malware in the wild and trying to get it to avoid detection. Thank you for this question. So then we need to do something to make it harder to evade these these detectors. And I'm sorry, I'm going to keep hammering the fact that this is just a pattern, right? So if this was a machine learning component that did scheduling for the operating system, then somebody might be trying to abuse it to get more scheduling time, or to do denial of service on a specific process or something. Or so the point is, whenever we put machine learning in our system, we have to worry about these tricks that somebody can do to try to fool the classifier. So our approach relies on kind of something that was developed in the machine learning world called something funny. I'm going to try to remember it. Probably approximately correct theory. And what this theory discovers is that if there is some stochasticity in the responses that you get from a classifier, then your ability to reverse engineer it is limited as a function of the stochasticity. It kind of makes sense, but it's sort of formalized. So what we did is we built different malware detectors, and then we stochastically pick one of them to classify a particular period of runtime of a program. And then the selector gives me an output. And then for the next period, I collect the features, which are, my events, like, again, memory distribution patterns, instruction distribution patterns, cache hits and misses, branch predictor statistics. So features like this, low-level features that are below the semantics of the program. But I use a different classifier to get an answer on whether it's malware or not. And then, provided that these classifiers disagree, then this adds uncertainty to the reverse engineering that the attacker is trying to do, right? So I do this over and over again. And we built these different detectors by varying the features that they use and by varying the length of the detection period, how many instructions before you apply your classification. And then it turns out, so I have like 4 combinations of this. So this one uses 2 detectors with 2 different features, or 3 different features, or 2 features and 2 detection periods, or 3 features and 2 detection periods. If there is no attack, I'm just using a different detector every time, and my performance remains good. If I have the attack that kind of injects a single instruction with every basic block, then you can see that we get a protection. So the high bar means that I continue to successfully find the malware. And the advantage increases with the amount of diversity that I'm adding, the number of different detectors that I have. And then if I even inject 10 instructions with every basic block, so kind of a crazy intensive attack, a basic block is usually only a few instructions, then I continue to have like very good detection with high diversity. So this seems to work, but the thing that it disables is the ability of the attacker to reverse engineer the detector. If the attacker knows the detector, then they can still craft things to evade it. And there are other ways to harden these kinds of detectors. So one technique that's really promising called adversarial hardening, where you expose the model during training to examples of the malicious behavior. And then essentially these areas that are don't care get filled up, and it learns to discriminate between even when people are trying to evade detection. Okay, so that's my first example, right? And the message is, let's not use machine learning blindly. We have to think about what people can do to avoid detection. The second sort of pattern that I want us to look at. So I talked about these microarchitectural attacks that you're able to do from the hardware to exploit vulnerabilities in the hardware to get information or to compromise a software application. And in this work, we try to use an attack called side channel attacks to spy on a machine learning model as it runs on a GPU and to use the information that we extract to steal the model, to kind of take the information that we can from this model. And if you remember, the model is a valuable piece of IP that the owner doesn't want us to steal. So in this case, we have a GPU that is either running on your desktop or your phone or whatever, or it's a cloud GPU. So if it's on the cloud, then it's an NVIDIA GPU. We use CUDA to program it, for example, or OpenCL or something like that. And if it's kind of a customer-facing GPU, we have something like OpenGPL or WebGPU or something like that basically we use to program it. And what we did in this attack is exploit different sources of leakage. So, for example, the GPU has a fixed amount of physical memory. And before you run, your application might want to determine how much memory is left to decide whether it can fit or not. So there's an open API that you can query the amount of available memory. Of course, you could run your application and measure the time, and the timing can be a source of what we call leakage, so giving you information about other applications. And finally, the GPU has a rich set of performance counters, right? All the GPU manufacturers include so much information, again, because the execution model is so kind of different than what we're used to, right? It has huge parallelism. All kinds of things can affect the amount of throughput that you get. So they provide a lot of information that you can capture. In the previous ID, we used it to protect the system, but here I can use it to understand what the application is doing and infer information about what it's doing. So I'm going to skip this, the slide. So we had to figure out, when we use the GPU by multiple applications, how they share the GPU. But suffice it to say that there is sharing, and we can kind of control the sharing so that I can spy on what some other application is doing. And I can spy from OpenGL on what's happening in CUDA. I can spy from CUDA on what's happening on OpenGL. And I can spy, of course, between OpenGL to OpenGL or CUDA to CUDA at the same time. So I could deploy a spy on the cloud. And then when somebody runs a machine learning model, I can try to figure out the details of the model that way. So we built a bunch of applications on this. So kind of one attack unrelated to ML is to spy on somebody as they're browsing the web. So I can kind of keep probing how much memory is available on the GPU. And then as a user browses google.com versus amazon.com versus facebook.com, they're rendering different number and different sizes of objects, which gives us a signature for the page. And then I'm able to, if I sort of browse them on my own and build the signature, I can then spy on you as you're kind of using the GPU as you're web browsing, and figure out which pages you're accessing. So let's say I found that you're on facebook.com now. I can start tracking which pages you are on facebook.com. So the accuracy is really high among the Alexa top 200 websites. But I figured out that you were on Facebook. Then I can see that basically, since the window, or I'm sorry, the tab, let me say, gets refreshed every time you press a button, I can see a dip in the rendering time. So this is the time interval between samples that I get that refresh the screen. I can see that the password that you typed is 6 characters in this case. And then I can use the timing information to do something called the keystroke timing attacks, or a known attack in security that leverages the fact that the keys are kind of have different spacing on the keyboard. So the time that it takes you to move from one key to another key can give you some information about what the second key was, for example. So I can use that to recover your password accurately. So the part that's interesting is using this kind of attack to spy on a machine learning model. So in this case, we had a kind of a toy benchmark, like a backpropagation application from Rodinia, so a training application. And we were basically measuring the performance counters to try to see what is the size of the model. So the spy runs and then creates contention with the machine learning model, which creates signatures in these performance counters. And then I keep sort of sampling these performance counters. Every time the spy kernel ends, it gives me a set of performance counters, then I can launch the next one. And in this case, I think we were trying to understand how many neurons were in the network that we were, that we were doing the backpropagation on. And then basically by just sampling for a bit, we can guess the exact number of neurons with the accuracy that you see on the screen. So again, it was not the most sophisticated attack. There's been a lot of follow-up work in using these kinds of leakages to do model extraction, but this was one of the first papers, I think in CCS 2018, we published this work. And now, it's accepted that these kind of hardware vulnerabilities can help you accelerate, these model stealing attacks. They can help you figure out the configuration of the model so that when you query the model, you can recover the exact model much more accurately and much more quickly. So the kind of the pattern that I wanted to emphasize here is that since we run on a system, the vulnerabilities of the system, we have to consider whether they can be used to amplify, the common attacks that we have on machine learning models, the types of attacks that I mentioned earlier in the talk. I don't know how I'm doing for time. I think 45 minutes. Is it okay to go 10 more minutes, or what's my budget? I'm sorry. Okay, I'll assume that 10 more minutes are okay. Sorry if I'm abusing your generosity here. The third and final pattern that I want to talk about is basically thinking of, so we've been thinking about building things like GPUs and accelerators like TPUs and so on, worried mostly about the performance or potentially about the energy efficiency of executing machine learning workloads. So the direction that I would like to propose is that we also think about building these accelerators to favor robustness as well, to take into account robustness. And there could be some interesting kind of opportunities if we think about building computing artifacts that are not just highly performing for machine learning, but also provide some extra protection against the types of attacks that we discussed. So
just
in this work,
just one
yes.
small bit of housekeeping. If you are an IEEE member, please type in the IEEE abbreviation in the chat so that I can make sure that I get an accurate count for membership.
Okay, great. So in this case, we were trying to see if we can build accelerators that by their nature are immune to those adversarial attacks. And we found that, one of the rare opportunities where you can have your cake and eat it too, or you can have your free lunch, or, pick your metaphor. So we found this interesting synergy between approximate computing and robustness. So basically, the techniques to make systems robust to adversarial attacks include adversarial training, where we, as I mentioned, expose the model to a lot of examples of what is wrong so that it learns to recognize them. But this is both extremely expensive and not fail-proof. It raises the bar, but the attacker can still look at the hardened models and find the blind spots in that model. And then we have techniques that we try to sort of do what is known as smoothing the model. So a lot of these attacks rely on gradient descent to find these weak spots. So if you sort of add a little bit of noise to the model, then they can hide these gradients and make it hard for them to converge and find adversarial examples. But it doesn't defend if you have access to the model, if you know the internals of the model. And then finally, there are runtime defenses, things like spatial smoothing and median filtering, that try to add noise to just the input or stochastically adapt the model or do things like that. So then, all of these can be computationally expensive and have limitations in how much they can protect you. What our insight is, and it was surprising, is that if we use approximate computing, so approximate computing is a type of computing where we allow errors. So I can, for example, lower the voltage on a circuit, so it consumes much less power, but it can sometimes have errors. Or, for example, if I have an expensive multiplier, I can replace it with kind of a simpler circuit, but it's not exact. It introduces errors. And it turns out that if I introduce these errors, then the model is a lot of the time tolerant to these errors. Since the circuit is simpler or it uses lower voltage, it also consumes much less power and is faster to execute. And at the same time, it ends up defeating adversarial examples because they rely on carefully crafting these sort of noise patterns. And then once they go through an approximate circuit, then it messes with them to the point where these adversarial examples, a lot of the time, fail to continue to work. So what we did is, so this was a paper in AskPLOS in 2021, if you're interested. And since then, there's been quite a few papers that used alternative approaches to approximation. But we focused on the convolution operation, which is critical to a lot of machine learning structures like CNNs and so on. So it basically does a convolution of a mask over a window in the image. So it's a lot of multiplications and additions. So what we did is we replaced the multiplier. So this is kind of a traditional multiplier that uses full adders with a really approximate implementation of the full adder. So instead of sort of the textbook full adder that you see on figure A on the left-hand side, we use something that is almost silly, right? So we pass the B bit as the sum, and we pass A as the carry. And we just ignore the incoming carry. And then we build the multiplier using these really, really simplified adders. So this figure shows the exact multiplier output. And then this is the output that we get through our approximate multipliers. And then the bottom figure is the difference in value, right? The error that we get. So there is kind of a recurring pattern of error depending on the exact values that you are multiplying. So the first thing that we tested is when we built, in this case, a small network. So this is a hand recognition network, typically used for MNIST, for example, called LeNet5. It's a small few-layer type network. And then AlexNet is a bigger network that is, for example, often used to implement image classification and so on. So when we built the circuit with the exact multiplier, so this is my default implementation, this is the accuracy that I get on normal images, not adversarial images. So you see that there is like barely a drop in accuracy. And this was obtained without retraining. So we train with the normal network, and then we plug in our much simpler circuits in its place. The attacker can also know that we are using these multipliers, so we are not assuming any secrecy in terms of what is going on. So the attacker can take a clean input and then generate an adversarial example and then see if it transfers to our network, or they can actually be aware of exactly what our implementation is and then try to generate an attack against our own implementation. So we tried a bunch of, so in these tables, the CMW and PGD and HSJ and so on. So these are names of different algorithms to produce adversarial examples. So CMW is Carlini and Wagner, perhaps the state of the art, a very kind of complicated optimization-based framework that produces an adversarial example with minimal weight. So if you can see on the exact network, they had 100% success in fooling the classifier. So 0% were classified correctly. And then when you run them through the approximate multiplier version of the network, it was remarkable, resilience to the attack. So the attack, succeeded with I guess 28% for PGD, but only 1% for Carlini and Wagner. And on a bigger application on image recognition, we still got pretty good protection just by using the approximate multipliers. And this is, remember that this is sort of a much cheaper circuit. So we got both a faster, lower power design, but also something that is robust to these adversarial attacks. So we try to understand why this is the case, right? So it feels too good to be true. So one of the things that we saw is that with the approximate model, the confidence in the correct class was much higher on average. And the exact model had a lot more uncertainty in the output of the model. So it sort of makes it more confident about what it's doing and then requires more energy, more noise to fool if this is the case. In the white box attack, we just apply the attack on the circuit, on the modified network itself. So what we should know about these attacks is that if I can add infinite amount of noise, then you will fool any defense. And my proof for this statement is I can simply take the image of the plane that I changed to be classified as a cat and just replace it with a cat. And then I can say, okay, I turned the plane into the cat, but it's not very interesting. So then when I'm developing these adversarial attacks, there is a sense of how much noise do I have to add? And the more the noise, the more observable and detectable the attack is. So when we give them access to our network to generate their attack, we know that eventually if they add enough of the adversarial noise, they will be able to fool it. But the question is, does it raise the bar in terms of how much noise you need to be able to fool the classifier? And as you can see here, if you keep adding noise and until you fool the approximate error, so the mean square error on the image that you produce is much higher for the approximate model. So that means you need to add a lot more noise to be able to fool the classifier. And conversely, if you measure something as the quality of the image, PSNR is a common metric, you'll see that the quality of the image that fools the approximate model is much lower because you have to add a lot more noise to fool it. So the advantage seems to be real. So even if you do the white box attack, you need a lot more noise to be able to bypass the protection that you get from approximate computing. And of course, approximate computing is much more efficient. So as I mentioned, this is like a win-win-win proposition, like rare. I still kind of want to make sure that we did not miss anything. But you end up using 40% of the energy of the full multiplier circuit implementation. You end up having a sort of response time that is only 25% of the full, of the full circuit. So the middle bar is some other multiplier implementation that is a little bit more accurate. And then this energy delay product, which is just the multiplication of these two, you see that basically you're about 10% of the energy delay product, while being equally accurate on clean images and providing robustness on these adversarial images. So what is the pattern here is that if we're creative and we think about building computing artifacts, not just for performance and energy efficiency, but also for robustness and security, we might end up kind of making some headway in making these machine learning models more secure. So I am pretty much at the end of my talk. I hope I convinced you that there is a need for some thinking and some research at the intersection of these three areas that we as a computing community, not, to sort of discriminate. So as computer engineers, let me say, we have to take some of the credit for this kind of unbelievable success of machine learning models, right? Because it is enabled by computing. But then as a result, computing is part of the stack, and we have to think about security as it intersects with architecture and systems, when we build machine learning support. So I gave you 3 examples, and they're kind of, I apologize that they're selected to mirror some of my work because I'm more familiar with it, so it's easier for me to talk about it. But I don't. I'd like to just clarify that I'm not claiming credit that our group is the only one or even the first one to sort of flesh out these ideas. But basically just think of them as examples rather than me presenting our work. And I think each of them is like a pattern or has a sort of a deeper lesson of something that we can kind of dig further and think about in a broader context of just the system that I presented it in. So as a result, I guess my pitch is that there's a lot of other research cross-pollination possibilities among these three areas, especially as machine learning continues to evolve at breakneck speed. So thank you for your attention, and I'm happy to take any questions. Sorry, I should show some of my collaborators and students. Yeah, I get to take the credit, but they do all the work.
So as our speaker has mentioned, we're going to open it up for questions tonight. And it looks like you've got some questions coming in through chat.
Yeah, Victor, I guess adversarial comes with the territory if you're thinking about security. Sorry, did I miss your question, Kurt? I'll go back to your comment. So yeah, so both I think in the specific sense of these like crafted examples that fool machine learning, right? So they're similar to these visual illusions that I showed that fool us, except there is a way to kind of systematically kind of develop them, and then these models don't know any better, right? They go ahead and misclassify, and then I can use them since they control real systems and control kind of outcomes. Then that gives me an opportunity as an attacker to mess with your sensor a little bit and then cause problems to my advantage. So yeah, both in the specific sense, I think it's an important attack modality that, I mean, really we're making some headway, but we haven't solved. But then in the broader sense, I mean, if you're thinking security, you want to think adversarial. I'm sorry, I'm not familiar with Thevenon's theorem. Could you say a word or two about that? Maybe I should Google it. So maybe meanwhile I can go to Jean's question. So is there work on AI designs its own defenses? Yeah, that's a great question, right? I think it's both an opportunity. So there is some work on that, but then if you think about like an adversarial opportunity, this feedback loop could amplify it. So you could cause like a small shift at the first point, and then that amplifies as you bounce back and forth between kind of machine learning models that talk to each other. And I'm looking at issues like this with the integration of multiple machine learning models. But to go back to your question, maybe so there is a type of kind of machine learning model called generative adversarial network. I'm not sure if you're familiar with it, but you kind of create two competing models. One of them is called the generator, and one of them is called the discriminator. And they keep kind of testing each other. So the generator generates an example, and then the discriminator is either fooled or not fooled. And then if it's fooled, it learns something and then feeds back the information, and they keep kind of bouncing heads against each other until they manage to kind of really train each other to work well. So there have been people that have applied GAN and similar technologies, including some of the work that we did, to kind of quickly sort of familiarize a machine learning model with all the different ways that it can be fooled, for example, and get it to explore the feature space better. Okay, generalizing a black box as a basic LRC circuit. Okay. Yeah, I'm sorry, Kurt. I am an electrical engineer by training, but it's been a while since I've worked with circuits myself. So
yeah, my apologies. It's just rather abstract in what I'm saying. And like you, I graduated a long time ago, so I just remember that. So I may not be using the concept entirely accurately. But I found your brief very interesting. I was like, fascinating.
Thank you so much. Thank you so much. But I would look up Thevenin's theorem and think about it. Yeah, thank you for
Okay.
bringing that up.
You're welcome.
Yeah, so AlphaGo uses reinforcement learning. Yep. Right. So reinforcement learning, you try something, right? You try a strategy in the game, and then if you win, for example, you give yourself a reward. So that's something cool. So just like you know, perhaps you raise a child, and then you tell, you know, every time they do something good, you praise them, and then every time they do something bad, you give them a you know, a timeout, or I don't know what the mode of penalty now is. So they get to learn quickly about what is like desirable behavior and or, you know, maybe advantageous behavior in the case of AlphaGo. Versus something that is not advantageous. Great, thank you for the pointer, Dr. PFR. Yeah, so the paper that I saw on adversarial attacks was not on AlphaGo. So it was on, I think, like a state-of-the-art new system called CocoGo or something like that. So I assume something that is, you know, a lot beyond, you know, a lot beyond what reinforcement learning is. So I personally don't look at attacks on reinforcement learning yet, but I'm happy to talk and get your thoughts and see if there's an opportunity for us to explore those. I agree. Carlini and Wagner is cool. Thank you so much.
I think we have time for maybe one or two more final questions. If anyone has any additional questions, if not, then we'll go ahead and end this session tonight. Thank you for your time tonight as the speaker. It was a thoroughly enjoyable topic. And, you know, I'll just leave it here for a minute or two and just see if anyone else has any questions.
Yeah, thank you so much, Michael, for inviting me. Thank you, Cooper and Gene. Thanks, Becky. Thank you. Thank you, John, UA, AA, Peter, Rajesh, Ibo.
Okay, so to answer the question about the recording, it has been recorded. It will be made available via YouTube. But just know that it can take a couple of days for that to get processed from the Zoom recording, converted to a format that YouTube can actually accept, and then go up to YouTube once all that's taken care of. So obviously I'll shoot for as quickly as I possibly can manage it, but it could be a little bit it could be a little bit of a wait. So if you're someone that did not register and you are wanting a link for the link to the YouTube video, please put your email in the chat so that I'll know who to send it to. Because the only mechanism I have at this point is to send stuff to people that have registered. So I'll keep it up for a minute or two longer, just on the off chance that anyone else would like a copy, would like a link that did not register. It is certainly a public video. Let me hang on one second, and I will post the YouTube channel information in the chat. So just bear with me one second. Actually, You're actually one of the first to actually ask about that. So just hang on 1 second and I'll get you the link. Let's see. So this should be. There we go. All right. So I have now posted the YouTube link, the general YouTube link in the chat. So you can certainly go to that. Just know, even though I do try to get these up as quickly as possible, it can be just a couple of days to work its way through the process. All right. Well, I think we had a very good session tonight. Thank you for your time. Oh, you got a question about slides.
I'm happy to send you the slides, Michael, if you can share those too, or I mean, I can share them through the chat also if that is helpful.
Okay.
Access to file restricted by your account admin. I'm sorry. So I guess we'll have to do it the slow way. Michael, do you have a way to share them?
Yes. I can. if you send them over to me, I'll find a way to get them posted somewhere.
Okay, I will do that. Right. Yeah, thank you again for the invitation and for your attention, everyone. It was very nice to spend some time with you.
All right, everyone, have a good rest of the night. This is the end for Careers in Tech Summer Series for July 20th. And the next session will be on July 27th. So next week. Have a good night, everyone.